Hello, this will be a video of the midterm review sheet going through these solutions here. Technically, this is lesson 13. The actual exam will contain approximately 10 questions, give or take. All right, first question up. A die is rolled 7 times. Find the probability of rolling a 6 exactly twice. So this fits the binomial distribution. We have a fixed number of trials, 7. We are finding the probability of rolling a 6 exactly twice. So we have two outcomes here, either getting the 6 or not getting the 6. So we can fit it into a yes or no situation. The number of successes is exactly twice. We're going to assume that each roll is independent. The value on one roll does not affect the value on any others. And the probability is fixed for any value when you roll a die. The probability is the same. It's 1 out of 6. So n is 7 trials. Number of successes, x is 2. Probability of success in a single trial is 1 out of 6. So plugging into the formula, it's 7 choose 2, 1/6 to the second power, and then the opposite probability, 1 minus 1/6, 5/6 to the fifth power. These exponents have to add up to 7. We have 2 successes, 2 rolls of 6, and the other 5 will be something else. So it's 7 choose 2 times 1/6 squared times 5/6 to the fifth power comes out to about 0.2344. All right, second problem. A zoologist is studying the number of times a rare kind of bird has been sighted. The random variable x is so we're calling x the number of times, the number of times the bird is sighted every month. We assume a Poisson distribution with a mean value of 2.5 times. So that's 2.5 times per month. Find the mean and standard deviation. So for the Poisson distribution, the mean and variance are the same, and that was given as 2.5. The standard deviation, you take the square root of the variance, so it's 1.58. All right, now, find the probability that exactly 5 birds are sighted in 1 month. So we're using the Poisson distribution, probability mass function, probability that x equals x is equal to e to the minus lambda times lambda to the x over x factorial. Lambda is 2.5. Lambda is 2.5, and x is going to be 5. Let me just write that in here. So lambda is the mean is 2.5. So we plug in 2.5 for lambda. We plug in x is 5. Exactly 5 birds, x equals 5. That's e to the minus 2.5 times 2.5 to the fifth divided by 5 factorial, which is 0.0668. So the probability that exactly 5 birds are sighted in 1 month is about 6.68%. Find the probability that 2 or more birds are sighted in a 1 month period. So 2 or more means 2, 3, 4, 5, 6, 7, 8. So that's too much to count. We're going to do the opposite probability. We're going to do the opposite probability, which is less than 2, 0, or 1. So we're going to count those out and then subtract from 1. So the probability that at least 2 greater than or equal to 2, excuse me, probability of x greater than or equal to 2 is 1 minus the opposite, that it's less than or equal to 1. Less than or equal to 1 is either 0 or 1. So we're going to count those two out and then subtract from 1. So the probability that x is 0 is e to the minus 2.5 times 2.5 to the 0 over 0 factorial plus e to the minus 2.5 times 2.5 to the first over 1 factorial for the case of exactly 1. 0 factorial is 1, 2.5 to the 0 is 1, so the first term is just e to the minus 2.5. 1 factorial is 1, so the second term is 2.5 e to the minus 2.5. So you could combine those and get 3 copies, or you can plug that into the calculator using the E button on the calculator. It's 1 minus 0.2873. It's about 0.7127 for the probability that 2 or more birds are sighted in a 1 month period. All right, number 3. We're given the CDF, the cumulative distribution function, and we're asked to find the PMF, the probability mass function, and then find the expected value. So to go backwards here, we're basically looking at the jumps here. This is a discrete situation. We're looking at these jumps, and those are going to correspond to the non-zero probabilities. So we're looking at these jumps here. So now we have to be careful with the scale here. There are 5 boxes to get to 0.25, so each box is a quarter. So that first jump is a quarter. The second jump is 2 boxes, so that's going to be 0.5, and then again a quarter. So again, this is 0.25 for 1 box. Then this one, we have a jump here of 2 boxes. That's 0.50. And then again, the last one, that's 1 box, so that's 0.25. So when did these jumps occur? The first one occurs at 1. So that's telling us that the probability of 1 is 0.25. The next one occurs at 3, and that jumped by a half. So the probability that x is 3 is 0.5. And then at 4, it jumps by a quarter, another 0.25. And the total is 1 whole. So this is recovering the PMF. So what are the values here? We have a jump at 1, and it jumped by 1 box, which was 0.25. At 3, we had a jump of 2 boxes, which was 0.50. And then at 4, we had a jump of 1 box, 0.25, for a total of 1 whole. So that gives us the PMF, and then they want the expected value. So we use the formula for that, which is the sum of each x times P of x. So we're going to do 1 times 0.25 plus 3 times 0.50 plus 4 times 0.25. And that comes out to 2.75. So that's the expected value or mean of this variable is 2.75. All right, number 4, probability distribution of the claim sizes for an auto insurance policy is given in the table below. Calculate the percentage of claims that are within 1 standard deviation of the mean claim size. So we have to calculate the mean and standard deviation here. We have to do the expected value. So that's going to be the first step. Summation x times P of x. So you're multiplying each claim size with its corresponding probability. 20 times 0.15, 30 times 0.10, 40 times 0.05, and so on. And you're going to total that all up. And that gives you a mean of 55. Mean claim size of 55. Now we have to find the variance here and then take the square root to get the standard deviation. So we got to find the expected value of x squared. So it's the same calculation as before, except we're squaring the x's first and then multiplying times the corresponding probability. So it's the exact same calculation, but each x value is squared first times the original probability. And so when you do that out, the expected value of x squared comes out to be 3,500. Putting that into the formula, it's going to be 3,500 minus the 55 we just found squared. So 3,500 minus 55 squared is 475. That's the variance. To find the standard deviation, you take the square root of that, and that's 21.79. So now the question is asking to calculate the percentage of claims that are within one standard deviation of the mean claim size. So the mean is 55. We're going to go one standard deviation out from there. So we're going to go up and down 21.79. So from the 55, we're going to go up and down 21.79 and then count what proportion is within that range. So we do 55 minus 21.79 is 33.21. 55 plus 21.79 is 76.79. So we're going to only count the x values in between those bounds and then count up the corresponding probabilities. So the numbers that are within those that range, 33 to 76, that are on our list are going to be 40, 50, 60, and 70. So those values are within one standard deviation of the mean. And so we're going to count up those probabilities, 25 plus 10 plus 10, it looks like 45. So it's approximately, it's 45%. So the percentage of claims that are within one standard deviation of the mean, it's 0.45 or 45%. So to regroup here, we had to find the mean, the expected value. We had to find the standard deviation, so we found the variance, which is e of x squared minus the mean squared. So we had to calculate e of x squared, then use that formula to get the variance, take the root to get the standard deviation, go up and down one copy of the standard deviation from the mean, up and down one, minus 2179 plus 2179. That gave us a range of 33 to 76 roughly. The values in that range are 40, 50, 60, 70. The corresponding probabilities were 05, 20, 10, 10 for a total of 45%. All right, number 5. A tour operator has a bus that can accommodate 20 tourists. The operator knows that tourists may not show up, so he sells 21 tickets. The probability that an individual tourist will not show up is 0.02, independent of all other tourists. Each ticket costs $50 and is non refundable if a tourist fails to show up. If a tourist shows up and a seat is not available, then you have to pay back $100, the ticket price, and a $50 penalty to the tourist. Calculate the expected revenue. So we want an expected value here. So we have to calculate the possible revenues, amounts that could come in, and their corresponding probabilities. So what can happen here? 21 tickets are sold. So we know that 21 tickets have been sold. So what's the situation here? If everyone shows up, then you have to pay a penalty to the one person that doesn't have a seat. If anything else happens, if one person doesn't show up, 2, 3, 7, 10, there'll be enough seats for everybody, and you'll just be able to keep all the money from the $21, 21 tickets sold. So case 1, if everyone shows up, we have to give back $100 because someone's not going to have a seat. So you get the $50 per ticket times 21, but then minus 100 for the one person that will not have a seat. And that's $950. Now, if less than 21 people show up, you get to keep all the money because you don't have to return the ticket and the penalty for someone that doesn't have a seat. If less than 21 people show up, everyone gets a seat and there are no problems, so you keep the full 1050. So the question is, what's the probability of this happening? What's the probability that everyone shows up? What's the probability that at least one person doesn't show up? So, what's the probability that everyone shows up? So, we were told here that there's a 2% chance that any individual person will not show up. That's 0.02. And it's independent of the other tourists. So we can use a binomial situation here. It's your call on which one you want to call P or Q. We're making P be the probability of showing up, which is 0.98. We want to know the probability that all 21 people show up. So N is 21 and X is also 21. All 21 people show up. So plugging this into the binomial, we're going to get 21 choose 21, 0.98 to the 21. We want everyone to show up, and then 0 people are going to fail to show up. So that's 0.02 to the 0 power. 21 choose 21 is 1. 0.02 to the 0 is 1. So it's just 0.98 to the 21, 0.6543. So there's approximately 65% chance that everyone shows up, and you have to give back $100. So that probability is 0.6543. And in that case, your revenue would be $950. Now, the probability of case 2 is the only other case. It's the complementary case. At least one doesn't show up. So we don't have to calculate that directly. We can just do 1 minus the probability of 0 people failing to show up. So this is the probability of at least one not showing up. It's 1 minus the probability that everyone showed up. So that's 0.3457. So there's a roughly 34% chance that 34% chance that at least one person doesn't show up and you get to keep all the money. So we do the expected value here. So it's 950 times the probability of that happening. 950 happens if everyone showed up and you had to return one of the tickets, and the penalty, that's 0.6543. The other case was at least one person doesn't show up. That was 0.3547. In that case, you get to keep all the money, all 1050. You multiply that out and add it up, $984.57. So that's the expected revenue for this situation. So again, a little bit tricky, a lot of wording here. There's 2 possible outcomes. Everyone shows up, you have to refund and pay the penalty. You lose $100 from the total that came in. You have $950. If anything else happens, one or more people don't show up, you keep all $1050. We found those corresponding probabilities and then did the expected revenue formula. All right, we'll split the video here and then pick up with number 6 in the next recording.